This is section 4.5, logarithmic functions. We usually just say log functions instead of logarithmic. Okay, logarithmic functions. The definition of logarithmic functions. Let a be a positive number other than 1. Then the logarithmic function base a, and it's noted like this, the word log with little subscript a, and it's read log base a, is given by y is equal to log base a of x if and only if a to the y is equal to x. Notice the value of a log, which is the y, is an exponent. Okay, so remember, a log just represents an exponent. So our note, again, a log is an exponent. When trying to evaluate a log, like log base 2 of 5, you're asking yourself, 2 to what power is 5? Okay, notice it's very hard to answer. So you're trying to figure out what power you need to raise the base to in order to get the argument of the function. So it's like 2 squared is 4, and 2 cubed is 8, so log base 2 of 5 is somewhere between 2 and 3. That's about all we know. So notice in general, you'd have to use a calculator. So terminology. Terminology goes with the definition. Number 1, y equal log base a of x is called a log equation. You know it's a log equation because it contains the word log. Number 2, a to the y equals x is called an exponential equation. We know it's an exponential equation because it contains an exponent. These two are equivalent. Okay, they are equivalent. Now we've worked with the exponential equations, so the log equations basically undo the exponential equations. So again, just keep in mind that a log is in fact an exponent. Okay, we have some illustrations of this. Number 1, the log base 6 of 36 is equal to 2 because 6 squared is equal to 36. Notice we can verify this. So if you take the base to the power that log is equal to, you're supposed to get what you're taking the log of. For number 2, the log base 2 of 1/8 is equal to negative 3 because if we take 2 to the negative 3 power, we get 1/8. And again, you can actually verify the exponential equation. And I've got one more illustration. The log base 10 of 100,000 is 5, since 10 to the 5th is 100,000. Notice in order to make these illustrations, I had to pick easy values to work with. Let's try some actual examples of doing this. We're going to convert between the log equations and the exponential equations. So some examples. Write an equivalent exponential equation for each log equation. So we're going from logs to exponentials. Now remember, the exponential equation, if it's all numbers, we can verify it. So here are my 4 examples. So notice, in 1 through 3, I do have nothing but numbers, so I better be sure that I can verify the exponential equation. Number 4, I just want to keep the same pattern going. So we really just need about 1 line of space to do these. So number 1, our solution. Okay, we actually make this little circle. We're starting off with log base 3 of 81 is equal to 4. So we're having 3 to the 4th power is 81. And notice that is true. 3 to the 4th power is, in fact, 81. Number 2, again, keep the same pattern. I'm going to have 7 squared is equal to 49. And 7 squared really is 49. The exponential equation is true. If the exponential equation you write down is not true, then it's wrong. Okay, for number 3, keep the same pattern. I'm going to have 5 to the minus 3 power is 1 over 125. And again, we can verify that. For number 4, just keep the same pattern going. There are no numbers, so we can't really verify it, so just keep the same pattern going. D to the t power is equal to W. Okay, D to the t power is equal to W. Let's go the other way now. We're going to go from the exponentials to the logs. So we really can't verify the logs, but the exponentials that are given as examples should be true. So write an equivalent log equation for each exponential equation. So we're going from exponentials to logs. So there are our 4 examples. Now, we follow the same little pattern that with the little circle that we make in the first group of examples, but you have to remember to say the word log. So for our first one, our solution. Okay, you start by saying the word log. So we have log base 2 of 32 is equal to 5. Okay, log base 2 of 32 is equal to 5. Okay, the base of the exponential is 2. The base of the log is 2, so the bases match. The exponent is 5. The log has to equal the 5. So the 32 has to be what you're taking the log of. Remember, the exponent is what the log is supposed to equal. For number 4, our solution, Number 2, keep the same pattern. Log base 4 of 1/16 is negative 2. Okay, so log base 4 of 1/16 equals negative 2. Again, the base of the log matches the base of the exponential. What the exponent is what the log is equal to, so the 1/16 is what you're taking the log of. For number 3, follow the same pattern. Log base 9 of 729 is equal to 3. So log base 9 of 729 is equal to 3. The base of the exponential and the base of the log match. They're both 9. What the log is equal to is the exponent. So what's all by itself? That's what you're taking the log of. For number 4, follow the same pattern. Log base n of m is equal to r. Log base n of m is equal to r. Again, the base of the log and the base of the exponential match. They're both n. What the exponent is what the log is equal to. And the thing that's by itself, that has no operation with it, that's what you're taking the log of. Part B, graphs of logarithmic functions. Doing the graph is also kind of going to illustrate what we usually do with logs. We're usually not familiar with logs, so we usually switch them to exponentials. So all of the graphs of y equal log base a of x will look alike, provided a is greater than 1. So we're going to illustrate what the graph looks like with a specific example. So we're going to graph y equal log base 2 of x. Okay, that's what we're going to graph, y equals log base 2 of x. So the equivalent exponential is, okay, my circle is going to go the other way because my log is on the right. 2 to the y is equal to x. So notice this equation is solved for x. So this is what we're going to use to make our table of values of. So since it's solved for x, we pick y, equation gives x. But remember, you're still going to plot x and y. Okay? Remember, we always plot x, y. So we choose y, equation gives x. So again, we pick y, equation will give x. So I started off with y being 0. Okay, 2 to the 0 is 1. So I plot 1, 0. Remember, plot the x first. 1, 0. Okay, for my second value of y, I guess I'll pick 1. 2 to the first is 2. But we're going to plot 2, 1. Plot x, y. So 2, 1. And let's go and do negative 1 for y. So x will be 2 to the negative 1, which is 1/2. I'm going to plot 1/2 negative 1. Okay, then let me do 2 for y. So x will be 2 squared, which is 4. So I plot 4, 2. 4, 2. Let's go ahead and pick negative 2 for y. And x will be 2 to the negative 2, which is 1/4. So 1/4 negative 2. Notice I'm getting closer to the y-axis. Now let's go and do the 3's. Y is 3. X will be 2 to the third power, which is 8. So 8. Ooh, I barely get it on. 8, 3. And then lastly, if y is negative 3, x will be 2 to the minus third, which is 1/8. So even closer to the y-axis. 1/8 minus 3. Okay, and then as best we can, we draw a nice smooth curve through them. Okay. Now again, provided our a is bigger than 1, they all look like that. So all the log base a of x look like that, provided a is bigger than 1. So some facts about this. If a is greater than 1, then the graph of y equal log base a of x looks like this. The only point we know for sure is 1, 0. They all pass through 1, 0. So properties y equal log base a of x with a greater than 1. Okay, actually this graph is one of the properties. So first property, passes through the point 1, 0. Second property, it's always increasing. Okay, again, going back to the graph, it's always increasing. Also notice, it's always concave down. So always concave down. So notice, it's increasing and concave down, so the rate of increase starts to decrease. It's increasing at a slower rate as you move through larger values of x. And number 4, it gets closer and closer to the y-axis, actually the negative y-axis, without ever crossing it. So the y-axis, which is x equals 0, is an asymptote or a limiting value of y equal log base a of x. And you also may have noticed that we couldn't give it any negative x's. Okay, we can't give any. We can't take logs of negative numbers. Common logs and natural logs. These are the two prevalent log functions that are out there: common logs and natural logs. Okay, we're going to look at two special log functions that have their own keys on practically all scientific calculators. Common logs. Okay, the definition. The common log function, noted log. Notice, there is no base given. It's log function base 10. So if you just see the word log, it's a base 10. We don't write the 10. So this means that log base 10 of x is just log of x. So with logs, if you don't see a base, it's understood to be 10. Okay, never write the base if it is 10. Just write log of x. And again, if you don't see the base, it's understood to be 10. This is the log key on your calculator. If you look at your keypad, so let's take out our calculator. If we look at the keypad, oops, let me get rid of my graph there. I don't need it. There is log. So examples. An approximate each of the following. Round your final answer to the sixth place. It is right at the decimal point. So I've got those three examples. Since I'm doing 6 places right at the decimal point, let me go ahead and set my float on the calculator to 6. So mode. Let's float on over to 6. Now, if you do this, don't forget that you've done it and undo it and set your float back to float and then quit. Okay, as long as I have it here, I want the log of 34,509. So press log. Okay, notice the calculator did open a parenthesis. So 3, 4, 5, 0, 9, close parenthesis. And we get 4.537,932. Okay. So 4.537,932. Remember what that means. If you take 10 to this power, you'll get roughly 34,509. Again, because we're rounding off, that's why it may not be exact. So remember, that's what it means. 10 to this power is going to be that number. For number 2, you're just going to do log of 789. Okay, so we're going to get 2.897077. So again, remember, 10 to this power is going to be about 789. And for number 3, you're going to do 76 log 410. If you want to put in the times, that you can, but you don't have to. At least not on the TI 83 and 84. So 76 log 410, you get 198.571573. So those are the common logs. Remember, the common log, log, is the log base 10. Natural logs. Definition. The natural log function, denoted ln, that's an L. ln in red, natural log, is the log function base e. We've been using e quite a bit, so now we know, well, we'll undo the e. So natural logs are also called Naperian logs, in honor of John Napier, the guy that developed all this. Okay, in today's language, Napier was actually doing the logs of the trig functions. So note that lnx is log base e. It is the ln key on your calculator. So again, on our calculator, there's ln. Okay, let me clear all that stuff out since I know I'm going to be doing some stuff later on. So approximate to the following. Round your final answer to the sixth place right at the decimal point. So instead of doing log, we're going to be doing ln. So again, I've set my float to 6. I'll just leave it there. So I've got natural log of 87.4 and 104 times the natural log of 218. So if you do this on your calculator, you'd have natural log. Okay, again, notice it open parenthesis. 87.4, close, enter. So I get 4.470495. So again, my float was set to 6. So 4.470, 495. Remember what this means. If you take e to this power, you'll get about 87.4. Number 2, you're going to do 104 ln of 218. You get 559.987, 487. So it's just a matter of which log key do you press. Now, some of the calculators, but not all of them, do have a log base B or a log base A key. Again, some of them do, some of them don't. So we need a way for those that don't, and I'm one of those that my calculator that I use by hand doesn't have it. So we need a way to evaluate other base logs, because remember, we still don't have a way to figure out log base 2 of 5. So the change of base formula. So we need a way to calculate logs of other bases. Again, most but not all of the TI calculators can do this without any real difficulty. Okay, for those calculators that cannot, there's a formula that we use. Okay, and the formula is called the change of base formula. We want to change the base from one that's not on the calculator to one that is. So we want to change it either base 10 or base e, so either the common log or the natural log. So here's the change of base formula. Log base a of x is the natural log of x over the natural log of a. It's also the log of x over the log of a. Notice what you're taking the log of is in the numerator, the base is in the denominator. Now, the intermediate calculations will look different depending upon which key you use, ln or log, but the final answer will be the same. So again, it's the final answers that are the same, not the intermediate calculations. Let's try a few. Approximate the following. Again, round your final answer to 6th place or right at the decimal point. Okay, my calculator float is already set to 6, so I'm good there. So here are our problems. Okay, we're going to finally figure out what do you take 2 to the power of to get 5, so log base 2 of 5, and log base 1/2 of 57. So our solution. So remember, log base 2 of 5, okay, I'm going to set my float to 6. According to the change of base, it's natural log of 5 over natural log of 2, which we get 2.321928. So remember, if you take 2 to this power, you'll get roughly 5. Now, just for fun, if you want to change the ln's to logs, you will get the same thing. So just to show you that, so let me clear this out. So if I do log of 5, close parenthesis, divided by log of 2, notice I get the same thing. Okay? So it's kind of like there really is only one log function. For number 2, you're going to have the natural log of 57 over the natural log of 1/2. And you're going to get negative 5.832890. You need the 0, otherwise you don't have 6 places. Now again, if you replace these ln's with logs, you'll get the same value. Now again, if your calculator doesn't have the log base B key, then you're going to have to do something like this. And again, the calculator that I use by hand doesn't have a log base B. But now some do. It's a matter of finding it. So your particular calculator may have a log base key. Okay, it'll actually say that log base. If it does, it will be in the math menu. So remember, the math menu, okay, let me clear this out. The math menu right there, math. If you press it, notice you don't see it right away, but if you scroll down, there it is, log base. Okay? If you remember it's A, you can go to it straight away if you can find the A key, alpha A there. So let's quit that. So again, your calculator may not have it. Okay, your calculator may not have it. If you don't see it in the math menu, then your calculator simply doesn't have it, and you have to use the change of base formula. So again, pressing the math menu gives me this. Remember, we had to scroll down, and there it is. Remember, it's choice A. So if you can do the alpha A key, then it'll pop up right away. So selecting the log base gives you this result. Notice you have to fill in the base, you have to fill in what you're taking the log of. So let's go ahead and do log base 7, that's 634.5 to 6 places. Okay. So that means I don't have to change my float. So if you press the math, scroll down to log base, and then press enter. Okay, I filled in the 7, I filled in the 634.5. So again, if I do it by hand, okay, so math. Now, if we know which choice A, so I can do alpha A. Okay, and then notice it wants the base first, and then use your navigation key to go and fill in what you're taking the log of. What am I taking the log of? 634.5. 634.5. And my float is still set to 6. Okay, let me get out of that. Notice the calculator opens and closes the parentheses for you. It doesn't do it on all the functions, but it does on this one. It's kind of strange. So there we get the same thing. So if your calculator does have that key, you can take advantage of it. Now, again, if it doesn't, you have to use the change of base formula. So remember what this means. If you take 7 to this power, you'll get 634.5, within round off. Okay, some properties and special values of logs. The special values means we don't have to use a calculator. Now, of course, you can, and the calculator will give you the special values. So before we do any application, we do a quick way to solve an equation that looks like this. 10 to the t power is equal to a number. Because of what we're going to be doing later on, that we have to be able to solve it. And also related to it is e to the t equals a number. So the solution comes from the fact that exponential and log functions are inverse of one another. So whatever one of them will do, the other one will undo it. So remember, the log function finds the exponent. That's what we're looking for. We're looking for the value of an exponent. So we also have the following. Properties of logs. Okay, properties of logs. Now, some people consider the change of base formula a property, and it is. So the first one, the log base a of a to the u is u. Okay, u stands for unknown expression. Remember, this is true because if you make your little circle, a to the u power is equal to a to the u power. Number 2 says a raised to log base a of u is u, because again, if you start with the word log base a of u is equal to log base a of u. Okay, again, in these two, the base of the log matches the base of the exponential. Whenever the base of the log and the base of the exponential match, they wipe each other out. Number 3, the natural log of e to the u is u. This is a special case of number 1 with a being e. Natural log and e wipe each other out. Okay, natural log and e wipe each other out. And the special case of number 2 is e to the natural log of u is u. Again, e and natural log wipe each other out. That's the net effect. E and natural log wipe each other out. We also have this version with the log and the base 10. So number 5, log of 10 to the u is u. So log and 10 wipe each other out. Again, this is a special case of number 1 with a being 10. And the special case of number 2 with a being 10 is 10 raised to the log of u power is u. 10 and log wipe each other out. Remember, 10 and log wipe each other out. E and natural log wipe each other out. We're going to use property number 5 to help us solve something. And of course, its other version would be number 3 if we had an e. So know your properties there. In order to solve the equation 10 to the t equals x, where x is a positive number, we use property number 5. Remember, it said log of 10 to the u is equal to u. Remember, log and 10 wipe each other out. So I'm going to start with 10 to the t equals x. Take logs of both sides. So remember, you can do the same thing to both sides of the equation, no matter how weird it is. I'm taking logs of both sides. So I have log of 10 to the t is equal to log of x. Remember, log and 10 wipe each other out. So this side is just t. So t is equal to log of x. Now, if I had e to the t equals x, log would become ln. Okay, remember, if you have 10 to the t is x, t is log of x. If you have e to the t equals x, then t is natural log of x. So whenever you're using an e instead of a base 10, log, it gets replaced with ln. So again, remember, the solution to 10 to the t equals x is t is log of x. Okay, so 10 to the t equals a number. The solution is t equals the log of the number. Okay, and we will need that later on. Okay, some special values. Again, your calculator can give these to you, but they're worth knowing without the calculator. So we have the following special values of logs. Okay, number 1, the log base a of a is 1. This is true if you make your little circle because a to the first power is a. Now again, this is true again because a to the first power is a. It's also number 1 from above with u equaling 1. Remember, if the base of the log matches the base of the exponential, they wipe each other out. The exponent you don't see is 1. And number 2, log base a of 1 is equal to 0 because that's a to the 0 is equal to 1. Anything to the 0 power other than 0 is 1. Again, your calculator can give those to you as well. So do you really have to memorize them? No. Now, there are many other properties of logs, but we don't need them for this course. If you were taking Math 1111, 1113, you would be shown them and you would have to use them. But for us, this is all we really need. That and what we saw in Part A, those 6 properties. And now, the applications of logs. In other words, the word problems. We're going to look at some various categories to help you out with some of the word problems that you might see in WebAssign, test, final, and so forth. So most applications, the reason we use logs or log scales is because the actual numbers involved are usually incredibly large. Okay, that was what Napier was trying to do. He was trying to find a quick and dirty way to turn large numbers into small ones. So the classic examples using logs are the Richter scale for earthquakes, the decibel scale for measuring sound intensity, and the pH scale for acidity. Now, in some of the examples, we'll give the background and formulas for how the measurements are using logs. In the actual printed class notes, I go into a little more detail about where they're coming from and how they're used. But here, we just want to learn how to solve the problems. So our first application, the Richter scale. Okay, the class notes have a little more details about the Richter scale. What we need to know is that a change in t units on the Richter scale means a change in strength or intensity of the earthquake by a factor of 10 to the t power. So if you're going from 3 to 4, you're actually being increased by 10 times stronger. Notice that's quite a bit. If you went from 3 to 5, you went 10 squared or 100 times stronger. So the Richter scale R of an earthquake is given by this. R is equal to the log of I over I sub 0. Where I sub 0 is the smallest intensity that can be measured, and I is equal to the intensity of the earthquake. Okay, I sub 0 is about the intensity of a small firecracker going off. Okay, notice you probably can't feel it, even if you're standing right there, but it's how much the earth shakes when a small firecracker goes off. So remember, this is its definition. Log of I over I sub 0. Let's try some examples. Number 1 says, on September 20th at 9:10 a.m. Eastern Time, a magnitude 5.4 earthquake struck Indonesia. At 12:21 p.m. that same day, a magnitude 6.1 earthquake was centered about 220 miles from Tokyo, Japan. Answer the following based on this information. Question A. How much stronger was the second quake than the first one? Round or final answer to the 3 places to arrive at the decimal point. Question B. What would the Richter scale read for an earthquake that is 1,000 times stronger than the second quake? Round or final answer to the nearest tenth. And question C. What would the Richter scale read for an earthquake that is 250 times stronger than the second quake? Round or final answer to the nearest tenth. Now again, B and C, the answers that we should get should be larger than 6.1. And notice the answer to B should be larger than the answer to C, because 1,000 times versus 250 times. It's the solution to Part A that kind of outlines what it is we do. So, our solutions. Okay, first of all, in step 1, find the difference in the Richter scale numbers. Okay, so remember we had 5.4 versus 6.1. So again, we're wanting to know how much stronger was the second quake than the first one. So it'll be second minus first. If we wanted how much weaker was the first and the second, we would do this correctly the way around. So find the difference in the Richter scale numbers. So I got 6.1 minus 5.4. We get 0.7. Okay? 0.7. Now remember, the Richter scale is a log scale, so we'll have to undo the log. So step 2, take 10 to the power from step 1 and round. So 10 to the 7th is about 5.012. Okay, again, you can verify that on your calculator. Okay, let me put my float back to float. So let me clear that out first. Mode, because I think I can round by hand. Okay, quit that. And then I had 10 raised to the 0.7 power. And again, to 3 places, 5.012. Okay. So the second quake was about 5.012 times more intense than the first. Okay, question B. Okay, we want a quake that's 1,000 times stronger than the one that measured 6.1. So this is the reverse of part A. I know how much stronger I want it to be. I want to get the Richter scale number. So first of all, we notice that 1,000 is 10 cubed. Okay, 1,000 is 10 cubed. You just count the zeros. Okay, that's what all you're doing. You're just counting the zeros. So that means the Richter scale number is 6.1 plus 3. Remember, back up here we did the difference, so since we're going backwards, I find their sum. So the Richter scale is 9.1. Notice that's an incredibly strong earthquake. Theoretically, they always claim that you cannot get a Richter scale number larger than 10. But there's always some theoretical ones that people say, oh, you can get 11. But theoretically, the maximum is supposed to be about 10. Now, question C is like B, except 250 is not a nice power of 10. So we want a quake that is 250 times stronger than the 6.1 quake. So I got to figure out 10 to what power is 250. So I want to find 10 to what power is 250. So I'm solving 10 to the t is equal to 250. Remember, that's why we looked at that problem earlier. 10 to the t is equal to 250. So remember, the solution is the log of 250. So the log of 250 is about 2.3979. I went a few extra places. So now do like we did up here. The Richter scale number is 6.1 plus 2.3979. So you get 8.4979, and if you round to the nearest tenth, it's about 8.5. Remember, we solved this problem, 10 to the t equals 250. We solved that earlier. Remember, 10 to the t equals a number. The solution is log of that number. Number 2. Find the Richter scale reading of an earthquake that is 6.3 times stronger than the smallest measurable quake. Round your final answer to the nearest tenth. Okay, our solution. Okay, we got our I is 6.3 times stronger than the smallest measurable quake. Remember, the smallest measurable quake is called I sub 0. So our strength is 6.3 times I to the 0. So we're looking for R is going to be the log of 6.3 times I to the 0 over I to the 0. Okay, the I sub zeros cancel. So we're looking at log of 6.3. And then if you take out your calculator and do log 6.3 and round to the nearest tenth, okay, you're going to have 0.8. Notice it's not a very strong earthquake. Georgia has been hit with quakes stronger than that. The decibel scale. Okay, so this is sound intensity. The decibel scale. Those that know your metric prefixes, deci means 1/10. The real measurement is called the bell. in order of Alexander Graham Bell. So the decibel scale is very similar to the Richter scale. It is used to measure the loudness of sound in decibels based on the intensity I of the sound. Okay, again, that's an I. The loudness L in decibels is given by L is equal to 10 times the log of I over I sub 0. Notice the difference between this and the Richter scale is this factor of 10. If we were to actually use bells, the 10 wouldn't be there. So now I sub 0 is the least intense sound that can be heard by the human ear. It's always been taken to be the sound of a ticking watch in a very quiet room that is 20 feet away from you. Now some people say, I don't think I could hear that, but that's always taken to be the least intense sound that the human ear can hear. Again, if you take away the 10, you have decibels, you have the loudness in bells, not decibels. So I is the intensity of the sound in question. Okay. Let's try some examples. Amplified rock music has a sound that is 10 to the 12th times more intense than I sub 0. What is the decibel reading? So our solution, okay, our intensity is 10 to the 12th times I sub 0. Okay, which is 10 to the 12th times I sub 0. So the decibel reading is 10 times the log of 10 to the 12th times I sub 0 over I sub 0. Okay, the I sub 0 is canceled. So we have 10 of log of 10 to the 12th. Okay, you can use your calculator to do a log of 10 to the 12th. Remember, log and base 10 wipe each other out. So this is just 12. So we have 10 times 12, 120 decibels. That's loud. Now again, if you did log of 10 to the 12th on your calculator, you'd get 12. Okay, number 2. A chainsaw has a loudness of about 110 decibels. Okay, that is the abbreviation for decibels, D with a capital B. What would be the decibel level of 3 such chainsaws? Round your final answer to the nearest whole number. For some reason, decibels are usually given in whole numbers, whereas Richter scale numbers are given out to the nearest tenth. Okay, our solution. Okay, the decibel level has increased by a factor of 3. So we need to solve 10 to the t is equal to 3. Okay, 10 to the t equals 3. So remember, from what we did before, t is the log of 3, which is about 0.477. So the decibel scale multiplies the log by 10. So we're going to have 4.77. You do 0.477 times 10. So 110 plus 4.77 is 114.77 to the nearest whole number, 115. Notice this is kind of like what we did with the Richter scale, except before we can add the two, we first have to multiply by 10. Because, remember, the decibel scale had the 10 in front of the log. Our next set of examples, the pH scale. This is in chemistry. The pH scale. So the pH scale is used to determine how acidic or how basic a solution is. Okay, pure water is considered neutral. So neutral is pH 7. The pH scale ranges from 0 to 14. Okay, readings less than 7 are acidic, and readings greater than 7 are basic. Most of us know about acids. Bases are most cleaning products. Most cleaning products are bases. So the pH of a solution is found to be, the pH is the negative log of this thing. Okay, this stands for the concentration of hydrogen ions. Technically, it's the concentration of hydronium ions. So you'll see chemistry books actually write it as H3O plus instead of just H plus. So it's the negative log. Okay, remember, the decibel scale had a 10 in front of its log. So this is the definition of pH. Some examples. Find the pH of the following substances. Round your final answer to 2 place to the right of the decimal point. Okay, question A, pineapple juice that has a hydrogen concentration of 1.6 times 10 to the negative 4, and mouthwash that has a hydrogen concentration of 6.3 times 10 to the minus 7. Most fruit juices are acidic. So remember, a pH reading between less than 7 is considered an acid. So for part A, I should expect something less than 7. So our solutions. Okay, remember, pH is the negative log of the hydrogen concentration. So for part A, I've got the negative log of 1.6 times 10 to the minus 4. Okay, here's my calculator thing. And to 2 places, 3.80. Okay, so the pH of this pineapple juice is about 3.80. Okay, for mouthwash, remember pH is negative log of the hydrogen concentration. Now mouthwash is considered a base. It's supposed to clean your mouth. So I'm going to have negative log of 6.3 times 10 to the minus 7. I give this to the calculator, and I get 6.200. Notice it's actually slightly acidic. So to 2 places, 6.20. Okay, so the mouthwash is slightly acidic, which is kind of contrary to most cleaning products being basic. Usually things that are acidic taste sour, and things that are basic taste bitter. Number 2. Solution A has a pH of 8.6, and solution B has a pH of 12.3. How much more basic is solution B than solution A? Round your final answer to the nearest whole number. This in some way should remind you of the earthquake problem. So our solution step 1, find the difference. So I'm looking at 12.3 minus 8.6. Remember, this is exactly what we did when we were looking at the earthquake problem. Then step 2, take 10 to that power and round. So I'm going to have 10 to the 3.7. Okay. And I'll answer to the nearest whole number. To the nearest whole number, 5,012. So notice solution B is about 5,012 times more basic than solution A. So very, very similar to the earthquake problem. Our last set of applications. Apparent brightness and magnitude. Astronomers use magnitude as an indication of the apparent brightness of a celestial object. Now some people say stars, but it can also include planets or whatever. So the relative intensity of a celestial object is a ratio of its intensity compared to a standard star. Astronomers have always used the star Vega as the standard star. Okay, Vega is not the brightest object in the night sky. It's also not the dimmest, but astronomers chose Vega. So I, which is the relative intensity, is equal to the intensity of Vega divided by the intensity of the star in question. So the magnitude, which is always little m, is 2.5 times the log of I. Now, it actually is very similar to the Richter scale and the decibel scale, because remember, this I is this ratio. Remember, for the Richter scale and the decibel scale, the standard was actually in the denominator instead of the numerator. So the brighter the object, the smaller m is, which seems contrary to what we would like. Okay, our sun, which is called Sol, has a magnitude of about negative 27. Again, it seems backwards to us that the brighter you are, the smaller your number. Okay, now, again, little m is apparent magnitude. Some of you might see capital M if you study astronomy. Capital M is the real magnitude. So, little m is apparent, capital M is real. Some examples. Solve the magnitude formula for I. We're going to need that formula for some problems that ask for I. They're going to ask for what is the intensity of the star. So remember, the magnitude formula is m is equal to 2.5 times log of I. So our solution. We're going to start with m equal to 2.5 times the log of I. Okay, I want to get I by itself. Divide both sides by 2.5. So m over 2.5 is the log of I. Okay, to undo the log, you've got to take 10 to that power. So we're going to solve 10 to the t equals a number. So 10 raised to m over 2.5 is I. Okay, so remember this little formula as well. We might need it. That I, the intensity, is 10 raised to the magnitude divided by 2.5. So again, this might become a useful formula for us. Number 2. At its brightest, Venus has a magnitude of about negative 4.4. How does the intensity of light from Venus compare to the intensity of light from Vega? Round your final answer 3 places right at the decimal point. You're like, how much brighter is it? Other than the moon, Venus is usually the brightest object in the night sky. So our solution. Okay, we used a formula from example number 1 with m equal negative 4.4. Okay, so remember we had I is going to be equal 10 raised to the negative 4.4 over 2.5 power. So if you take our calculator, you get 0.01737, etc. So to 3 places, 0.017. So the light from Vega is about 0.017 times as intense as the light from Venus. That's what that means. Notice, since the number is less than 1, that means Vega is not as bright as Venus. Number 3. If the light from a star is 3 times as intense as the light from Vega, what is the apparent magnitude m of the star? Round your final answer to the nearest tenth. Okay, our solution. Can I let x equal the intensity of light from the other star? Just to give it a name. Okay, according to the problem, x is 3 times the light from Vega. Okay, so x is equal to 3 times Vega's intensity. Okay, we plug this into our formulas so that little m is the intensity of Vega divided by the intensity of the star. Okay, and remember the intensity of the star is 3 times Vega. So the intensity of Vega cancels out when I get 1/3. Whoops, I'm sorry. That should actually be I, right? The intensity? My error. That should not be m, that should be I. I is equal to the intensity of Vega. It actually says intensity, doesn't it? So I is equal to intensity of Vega over intensity of star. So I is 1/3. So then m is going to be 2.3 times the log of 1/3. So remember, this should be I, not m. So you take out your calculator and do 2.3 times the log of 1/3. Oh, I'm sorry, that should be 2.5. I've got another error, don't I? It should be 2.5 times the log of 1/3. I have it right in the calculator. So you get, how far am I going? Here's tenth, negative 1.2. Okay, so again, that should be 2.5. Remember, the definition said 2.5 times the log of I. And remember, this is I, not M. So I is intensity of vega divided by intensity of star. So that's intensity of vega divided by 3 times intensity of vega. So I is 1/3. And M is 2.5, like it says here on the calculator, times the log of 1/3. So the apparent magnitude is about negative 1.2. And that's the end of section 4.5.